So I think it was Shakespeare, I'm pretty sure because I saw it on the web, who said, "There are more things in heaven and earth, Horatio, that are dreamt of in your web-centric systems of scale." We're going to look a little beyond that. A lot of the talks today, which I have intensely enjoyed, by the way, mostly dealt with those kind of systems. But we're going to go a little bit beyond that. And I hope by the end of the time, you'll be surprised at some of the things that you have seen, because some of you may have never seen some of these kinds of things. Here's how I can be reached. I'm easily available. Twitter, I'm active on it. Email me, happy to do so. The very first program is this one that Ada Lovelace wrote back in 1815 in the calculation of the Bernoulli numbers. Jump ahead 205 years and we have software that deals with this. We're talking about an intense growth in complexity and computational power. I'm sure many of you watched what happened here, but just the many single points of failure and the fact that there was software behind that driving it, I was on edge the entire time, and it's up there and it's great. By the way, the original work on this project, the James Webb Telescope by Northrop Grumman, they used the UML. So yes, it's well architected in that regard. But you know, if we even think of those 200 years and now project forward 200 more years, when your children's children will be debugging the code you write today, no matter what future you imagine, it's going to involve software that hasn't yet been written. And so in that sense, architecture is something we're going to see living beyond what we create here. At first, it's a statement of vision, but ultimately the architecture of every system is really built upon the billions upon billions of small and large decisions that are made along the way. So in that sense, some architectures are intentional, some are accidental, most are emergent, and really all the vibrant ones must evolve over time. It's not just software architectures that evolve. We see it in every human artifact. Some of the earliest structures from the Neolithic period, we're talking 10,000 before the Common Era, were largely mud and rock kinds of structures. That's really all they knew how to do. And indeed, even if you go to indigenous population in the United States, those were the structures that were built. The gate, by the way, is not an original one. It was added later. Other cultures later used the materials around them, such as what we see in Petra, where they didn't use the rock and mud, but they actually carved those structures from the rocks themselves. Move forward to Egypt some centuries later, and now mathematics and geometry in particular were playing a role, because they changed the ways that building could be built. There was now a possibility of building structures that were far beyond just a single structure like you saw before. Moved toward the Greeks, and they were well understanding the issues of geometry and mathematics, enabling them to build structures such as this. And then the Romans, of course, building amazing structures such as this. And now we're into the time of the Renaissance, where these structures, built without our modern tools, without modern mathematics, flourished. Remarkable what could be done around the tools and structures around them in truly long-lasting architectures. Those ideas continued not just to the religious space or the governmental space, but also the domestic space. And we found those structures moving inside as well, where now we had the free time, the free resources, the ability to amplify what was happening inside as well. Things radically changed in the Industrial Revolution when now all of a sudden we had completely different materials. The shift from rocks and mud to concrete, as the Romans were doing, and now to steel, enabled structures such as the Crystal Palace, which changed the way we built things, enabling structures such as the Empire State Building, and later, as we find in Abu Dhabi, these remarkable structures. If you look close, I think you'll see Tom Cruise hanging on the side of that one, if you remember his film. So we have come a long way in modern architecture. Tools also changes, not just material. The advent of structures within our ability to model let us now create ideas that we could then test out to see if the structures would work, if they'd handle the stress, wind, and all that. Such we were able to build things such as the Disney Concert Hall and amazing structures such as what we see in China now, which they've used for several years. And I think this is an amazing sense of architecture because not only is it functional, it is also beautiful, and all architecture, no matter what domain, aspires to do that. So you think of it this way: architecture advances as part of the coevolution of human need and technology. They both advance and they support one another. The same is true of software-intensive systems. It is fair to say that computing began with women. Indeed, women were the first computers. In the very front with the lens is Annie Jump Cannon, who was a human computer. These are the computers from Harvard in the late 1800s. Here we're only talking about 40 years after the time of Ada Lovelace. This, by the way, looks an awful lot like a stand-up meeting. So in fact, if you read any of the histories of these women and their stories, you will find that these were self-organizing teams. Agile concepts are not old. In fact, they go back to this time as well. There were no architectures per se. This was just pure mathematics. But as we started moving toward machines such as the ENIAC, then all of a sudden we were beginning to see structures. And again, I should mention women were leading the role here. As it was structured, ENIAC was not so much a programmable thing as you had plug boards, and the men, mostly the mathematicians, would say, hey, go calculate this thing. And the women, there were 5 of them in particular, who there are some wonderful oral histories about them, would go off in a corner and say, hey, how do we plug these things? They learned some interesting things about it, and they began to develop literally the first pattern language along the way. As we moved toward the 50s and 60s, and now we were dealing with algorithmic machines and algorithmic languages, now all of a sudden we began to see some very clear architectures. This is the range of the first generation, or the first golden age of software engineering, in which structured analysis and design methods came into play. And then, and this is where I began to come on the scene, we began to see the miniaturization of machines and the changing of languages, not just from algorithmic languages such as Fortran and COBOL, but to languages such as Smalltalk and Simula and eventually C++, which changed the notation and the means of expression to these machines. Then, of course, architectures changed as we moved to microcomputers, because now all of a sudden we weren't just lashed to a mainframe, but now we could distribute our systems where some of the processing was on the client, some was on the server, and the clients are becoming increasingly powerful. Our previous architectures were simply insufficient. And then, of course, the web came along. Ask yourself this question: when did you get your first email? I got my first email address in 1979, of all things, when it was still the ARPANET. So I've been around for a long time with this. And even back then, we were trying to develop distributed systems. One of the first things I was involved with was a project at Space Command before the previous president created such a thing at Vandenberg Air Force Base. We were building a system out of about 24 mini computers to fuse information from some 40 telemetry systems from around the world for the military shuttle program. It was quite fascinating. And the same problems we struggled with then for distributed systems, we're struggling with today. And then, of course, we moved to mobile devices, which changed the architecture of the systems we build as well. Where we're headed now is this space, where software increasingly moves into the interstitial spaces of our world, where it becomes invisible, as all good technology should be. And then, of course, this is on the edge of where we are. This is from the movie Her, representing the creation of artificial intelligences, AGIs in particular. And that is part of what's leading us to new generations. Now, to explain, as I will in a moment, how these new technologies of AI and eventually quantum are going to impact us, we need to go back to some fundamentals of how we think and approach systems. Architecture in the software space has advanced as part of the coevolution of computing and the human experience. They have resonated with one another, and it is where we are now. But as we think about computational thinking versus scientific thinking, there's a bit of a difference, and that difference is significant. The earliest ways of thinking evolved as a means of bringing certainty and predictability to an otherwise uncertain and very unpredictable world. And it began with the premise that we could understand the cosmos. It's not a provable premise, but it's a reasonable one, and it's a somewhat testable one. So we can look at the cosmos. We can ask, hey, if I drop this log and I do it again, why is that happening? Why are these stars moving in this certain way? Why do these chemicals react in the way they do? Then we can devise why that is the case. And indeed, in the end, we end up with the standard model of physics, which is, in a sense, the manifestation of the simplest laws we know that animate the universe. I'm going to say something you may find controversial, but I'll defend it to my life. Life is a consequence of the laws of physics. And furthermore, sentience is a consequence of the laws of physics. By implication, that means, yes, I believe it would be possible to create an artificial sentience. So scientific thinking evolved as a means of understanding the world, but the central premise of computing is the reverse of that. Its premise is that the world is computable. So we begin with not looking at the cosmos, but in a way we begin with the simplest of laws, the nature of the Turing machine, and the fact that if we can implement it on a Turing machine, then it indeed is computable, and we can take our vision from there. And from that, we can actually create our own worlds. We can't really see this in real life. This is a black hole, but it was created through the assemblage of thousands upon thousands of readings and partial images to give us this vision of it. So we are creating our own worlds through this. Computational thinking, therefore, we can think of as having evolved as a means of controlling the world from a fidelity once relegated to gods and goddesses. As it was said by Stuart Brand, we are as gods and we might as well get good at it. So I mentioned this notion of vision to implementation. We as software architects, we as software developers have this very simple role. We take things that we want to imagine, that's on the left-hand side, we turn them into reality, and that is raw running naked code. That's on the right-hand side. There are a number of things that separate us from those two. The first is the laws of physics. I can't move information faster than the speed of light. I might like to sometime, but hey, can't do it. It's also the case that I may need to devise algorithms, and if I don't understand that algorithm, then it's not going to be computable for me. The Viterbi algorithm is a great example of that it is the key toward pulling signals out of the noise of cellular communication. And we know that there are many other algorithms out there that we have theories about, but haven't yet made them manifest. We all here are talking about the world of architecture, which is in effect, how does one structure those pieces so that I can build systems that carry out my vision? And we realize it's not just a technical problem. We also have to deal with the organizational architecture, the fact that it costs to build these things, and ultimately we're dealing with human elements as well. So architecture fits squarely in the center of this, and in many ways, it is the linchpin, it is the tent pole, it is the center of all that we do. So there's another aspect that becomes relevant as we look at how architecture is impacted by new technologies. In computational thinking, we also make the assumption that cosmos is discrete. We have an understanding of the foundational reality of information, that we can look at the world and say information is based upon it. David Deutsch, in fact, will go so far to say is that the whole universe is in fact digital. We also view data as an abstraction of reality, and this is where the human factor comes into play, because we try to build abstractions that meet our needs as humans in the real world. We also believe in the power of algorithms to form those abstractions, and we also know about issues of scale. And here comes the kicker. It is also the universality of computing, meaning that symbolic, neural, and quantum models of computing are Turing equivalent. But they each have different advantages, efficiencies, and costs. I could do a classifier in Fortran if I wanted to. I could build World of Warcraft from a Tinker Toy set if I wanted to, as long as I had enough time and space to do it. The universality of computing means that I now have an incredible amount of expressive power in my landscape, and I have many more choices. So now all of a sudden, the palette upon which we as architects work is truly vast. Now, even though as architects, we love to talk about structures and patterns and diagrams and the like, ultimately it's all about the code. The code is the truth, but we know it's not the whole truth. I like what Stefan observes, that architecture is a property of a system. It's not so much a description of its design, it's really the property of it. Every system has one, some intentional, some accidental, they all have them. And David Cheney puts it, I think, in this great way. Architecture is the invisible things of positive value. And, bugs are the opposite of that. Features are positive things that are visible. Technical debt is invisible and it's negative. All great kind of things. And by the way, when I make these kinds of decisions, when I make these trade-offs, notice this is not a static thing, that the architecture at one moment in time may be just right and reasonably optimal, but the world changes around us, and thus the importance of coevolution. So in that sense, you've heard me say it before, this is my definition of architecture. All architecture is design, but not all design is architecture. Architecture represents the significant design decisions, where significant is measured by cost of change. And there are many cases where use case comes into play, where architecture comes into play. Every one of these circumstances, you will find a place where a focus upon architecture as an artifact adds value. It helps one actually build the system with greater efficiency and less risk than if I don't deal with it. And it's going to hurt you in the long term otherwise. So in that sense, for me, I've always seen architecture as an artifact important because it allows me to visualize, reason about, and document significant design decisions. Architecture is also a process because it incentivizes simplicity. It allows me to attack risk. It's a way of providing accountability. And furthermore, it contributes to institutional memory. I am currently on the largest project I have ever been engaged with. It is one that is expected to have a 50-year life cycle. It will take about 3 to 5 years of development. The code will live long beyond any of us on this call, most likely. And I know that the people writing the code today, they're not going to be around. And so institutional memory becomes actually an important element for us. And yes, by the way, it will evolve over time. Now, your mileage may vary in terms of architecture, and here's one way to think of it. Think of an XYZ grid. Along my x-axis, I've got just ceremony. Some organizations rightfully have different ceremony than others. If I'm dealing with a startup in the Valley, you don't need no stinking documents, you just build something in general. On the other hand, if I'm spending a few $1 billion of taxpayer money, I want to have a little bit more accountability, so it puts me a little further to the right. There's also the issue of complexity, the line coming toward us. If I'm building yet another Tinder, Grinder, whatever, built those before. Well, I haven't built them, but those things are understandable. We understand how to build those kind of systems. This is why we have frameworks and patterns to build them. So the complexity is low. If I'm building something nobody has ever done before, like a system to deal with protein folding, much, much harder. And then lastly, in the y-axis, this is the issue of risk. If I fail in my startup, I just lost some people money and I'll start over again. I'll stand back up and do it. No big deal. On the other hand, if I just created global thermonuclear war, this is generally what we speak of as in engineering as a very bad thing. So you want to apply a little bit more discipline along the way. This has been talked about in other presentations today, and I'll give you my form of it. All architecture is trade-off, as the previous speaker said. It's a trade-off based upon all these things, and it's not just static at this moment in time where I make this decision now because, hey, I've got to have this particular throughput, but you must build an architecture that is vibrant and allows itself to change. I urge you to read Stuart Brand's book, How Buildings Learn, in which he talks about the shearing levels of change in which I can architect a building, and it is long-lived insofar as I have clear separation of concerns among those shearing layers. Architecture is not a moment in time. Architecture is a process. So is Neil and Mark so rightfully say it depends for every one of those. I love that it was also mentioned in the presentation about the 4+1 model view. It is something I have dealt with for years since I had the opportunity to work with Philippe. It came, by the way, from his work with the Canadian Air Traffic Control System, and we found it worked so well on large systems, we just kept at it. Quick aside, reflecting on Len's presentation earlier with regards to DevOps, DevOps effectively covers the right-hand side. This is the view where I deal with both the components as well as the deployment that the DevOps people deal with. Notice I use the word view. This is all related to a larger concept from ISO, IEC, IEEE standard 42010. So the work Philippe did led to the creation of this standard on architectural description, which really codifies the notion of views and stakeholders. There are more than just business stakeholders, there's lots of different ones, and each of those stakeholders has different views. The 4+1 model view is one example of that. Another principle that I use are architectural description records. They're awesome, they're wonderful. They're a way that I can declare a particular decision made at a point in time, and now I can treat architecture as code, architecture as actually put into my repo, so that as I make the changes, it's there over time. And that way, if I put an ADR in, I'm saying, hey, here are my major decisions. People can come back to it later. I can see versioning on it. So between these two, the 4+1 model view and the ADRs, man, it works. So let's spend a few minutes on symbolic models of computation. Then we're going to look at neural models and then quantum models and see how those come together. So it really all began with this dude here in his book on the laws of knowledge, as he called it, Boole, in which he was trying to capture the basic ideas of logic. Now, he was a bit of chutzpah because he thought this is how we dreamed and how minds worked. Not quite right, but it's the way we began to architect our systems. And actually, many of our hardware systems came from that. The idea of being able to use relays that could do Boolean logic was essential to the growth of early machines. So the notations and architectures we would use in the 50s and 60s were, as I mentioned, around the notion of structured diagrams, because here the fundamental and really only unit of decomposition was an algorithm, a function, and not a function in the sense that we think it with today, like a lambda, a little bit different, just really a procedural kind of thing. And that's what the focus of architecture was. And the dominant problem was, how do I best decompose my system into these things? As we move to that cusp where we're no longer working with functional or algorithmic languages, but now object-oriented languages, you see structures like this. And I'm going to give you a quick example of a 4+1 model view. This is a logical view of Watson Jeopardy. And you basically need to understand a couple of dozen classes to grok the essence of the semantics of it. We reified things such as questions and answers and candidate answers. That's the basic vocabulary of the problem space, which is what that piece of it is all about. The process diagram says, how does this thing flow through time? So we're now looking for this from the top to the bottom, and we see that there are multiple agents, and these agents first do a question analysis, then they do a search and candidate and so on. Basically, it's a pipeline architecture is what it is, and this is what we represent here. If you look at it from the deployment view, the component view, where you're now seeing the components, how do we put these things in jars? Where are the frameworks we build upon? Always generally layered, it looks like this. And this becomes relevant because this is where I make design decisions about where my repos go, where my libraries are, where my services live as well too. And then lastly, we have the implementation view, which is where does all this stuff get put on our machines? And that's the diagrams we look at here. Well, there's another way to look at it. If you look at many web-centric systems, I find it deliciously wonderful that Amazon and the Kubernetes community and Microsoft and others are rediscovering the value of visual notation. This is the notation that AWS uses, and I've seen hundreds of these kinds of things and looked at them. They basically cover what cuts through the deployment of the implementation view, and they begin to describe the message passing and the major components that exist within such systems. They're reasonably valuable, quite useful. If you look at it from the view of services, though, it can get quite messy. Some brave soul took all the services from Amazon and Netflix and decided to see how they were connected with one another. You end up with like this, which of course we saw in previous eras as a big ball of mud. Yes, you can build those kinds of things in services as well too. But you know, there's a reason for this. All the Mangs of the world have done this. They've moved to containerized microservices because they have a problem that involves soft edges, but it requires elastic computing at scale. And there's a requirement for continuous integration and continuous deployment. But listen to this. Not every problem is the problem like these guys have. Not every problem is a web-centric system of scale. So you may look at them lovingly, but they may not necessarily be a solution to your problem. Build upon them, use their frameworks, build what you've learned from them, but your problems are not their problems. And remember, I also said that the world of software-intensive systems is more than just web-centric systems at scale, and there are more stakeholders than there are just business stakeholders. If I'm building something like an autonomous vehicle, uh, which, by the way, I think Elon made a fundamental system design decision flaw, and he didn't use LiDAR, but we'll see what happens. This is a good example of an architectural trade-off. He decided to shift the risk to software to save some money in the hardware side of it, and it's actually increased in the complexity of what he's doing. And even if I'm dealing with real-time things like that in systems of scale, many ways to look at scale beyond just what we see in the web. It might be number of simultaneous users. Well, we have some patterns to deal with that. Might be a number of concurrent transactions or activities. There are some architectural patterns to do that. I know there was right before this some discussion about Bitcoin and the like. If you follow me on Twitter, you'll see that I have been a rather vocal critic of what's going on here. Michael Saylor and I have a conversation coming up in about a week where he and I are going to come head to head on it. But if you look at things like Visa, they will handle some 1,700 transactions per second. There's a project Hamilton, Bitcoin handles, a few dozen per second or thereabouts at best. And there's now a project Hamilton coming out of MIT that's looking to build a digital currency for central banks, nothing to do with blockchain, which is reporting around several million transactions per second. Architecture is important. We also have to deal with trade-offs of volume of data, and there are clear organizational patterns to do that. But now when you start moving to hard real-time systems versus near real-time versus non-real-time, you're now dealing with issues of latency, reliability, fault tolerance, fail-safeness. It becomes nasty and hard. And there are some patterns, but this is indeed hard. Indeed, as you move to novel systems, architecture is harder because we don't have patterns upon which to build. You try things, you fail, you do it again. And it's also becoming really hard if I'm building systems of extraordinary complexity. So the good news is in the architecture world, at least in the symbolic world, we have some patterns upon which we can build. That's a good thing. And also the case, many domains, because we've seen them before, they end up being made manifest in frameworks. I say, hey, I need a message passing system and I need these particular characteristics. So I might choose RabbitMQ or I might choose Kafka. Again, as Neil and the others were saying earlier, it depends. So you got to choose one of those two, but hey, at least I've decided it's a message passing system and I don't have to build one of those from raw iron. That's good. And it's also the case that in the novel domains and the complex ones, you simply got to try stuff and try and fail and do it over and over again. Most of us are in the first world. And as we try new things, we move to the second world. And you've seen this process-wise. I mean, this is agile from me in a nutshell. The x-axis is time, y-axis is intensity. Every process involves a period of discovery, that's the red, a period of invention, that's the white, a period of implementation, that's the green, and they always overlap. And CI/CD, and I would add continuous architecture is what you see on the bottom, where you have this common flow of the heartbeat of a system. Whenever I get parachuted into a project, the first thing I'll ask is, what's your rhythm of releases? And they say, oh, it's every few days. It depends, and I'll whack them about the repo for a little bit, say, hey, let's fix this. Then I can begin to talk about other kinds of things. So as we think about looking back at the history of symbolic systems, this is where our architectural concerns were at first. They were just fundamental mathematics. How do I write this algorithm? How do I manage the complexity of these bunch of algorithms? As I move to PCs, how do I deal with human-computer interaction? How do I move to scale as I move to web systems? And now, in many ways, yes, we are dealing with ethical and moral issues. Architects must deal with these things. You're building systems that have an impact upon the people around you, and therefore ethics and morality should be an architectural implication. So we can conclude this by saying symbolic models of computation have advanced and will continue to advance, largely owing to real world use. But there's a different way of looking at the world. These are systems that reason and that learn. I spend about 50% of my day job working in AI these days, and it's interesting. I've got some AGI projects. I've got some easier ones dealing with fraud analysis and the like. kind of covering the spectrum and actually also doing some really interesting work with space. Last project I should mention is you may look up the Mayflower. This is an autonomous vessel going from the UK to the US, where I worked with some of the leading humpback whale researchers. And with the group in our Hershey labs, we trained an AI to identify humpback whale songs. So we trained it on the cloud, squeezed it down to a Raspberry Pi, and it's now coming across the Atlantic, seeing we can hear whales. But you know, the idea of an AI, it's an old one. Talos is perhaps the first conception of an AI we find in Greek mythology. He was this golem that walked around Crete and was built out of clay. Even Da Vinci had the notion of automated knights. War is a messy, dirty thing, so why not use mechanical knights along the way? And we've certainly seen this in our movies as well as of late, and of course things like HAL. One of the projects I'm on is in effect to build a HAL. In the mission to Mars, you can't take mission control with you. You can't use it on the ground. You have to take it with you because of speed of light issues. It's about a 17-minute round trip time to Mars. So you need an AI with you. That's HAL minus the homicidal elements. And we've actually been trying to work on that problem. Turing, of course, from the symbolic days also said, hey, you know, if we could build a system that we call it intelligence that we could deceive a human, wow, that'd be great. It's interesting that deception was an important piece of that intelligence, but hey, it's all about humans, right? The earliest pieces of AI came from the analog world, in particular Norbert Wiener, from whom we can coin the term cybernetics and all the cyber stuff that comes from it. And his ideas came from analog control systems, mostly around the time of World War II. We were dealing with homeostasis and the like. So you'll see his ideas based around that. But then there came onto the world a symbolic view of AI from Newell and Simon in particular, where they were taking some very theoretic ideas and see if they could do formalisms that were in fact intelligent. Feigenbaum came along in the next generation in what we call really the second winter of AI, dealing with knowledge-based systems, which was effectively if-then-else kinds of things. And that, by the way, led to an explosion in a certain kind of hardware, because our machines at that time weren't especially fast. Special machines were built, such as the list machine or the connection machine. And then we started seeing this in domains beyond just the formal ones, Deep Blue in particular, which showed that brute force methods were quite successful in giving the illusion of humanity. And then later on, Jeopardy, which was a very different way, as we described. It was mostly statistical methods of AI, and then using on top of that pipeline architecture. But there's yet another way, not just a symbolic, and that is neural methods. So back around the 40s, there was a gentleman who discovered the idea of how neurons actually grow and learn. This is known as Hebbian learning, that when you find neurons that fire together, they strengthen their connection. That's Hebbian learning and deals with the plasticity of the brain. That looked intriguing because we began to realize that neurons were potentially processing things. We have been able to model the entire neural network of the common worm. We are close to modeling the entire neural network of the entire brain. It's big, that's great, but we still don't understand its architecture. So as that work was taking place, then Marvin Minsky and crew said, hey, can we turn this into hardware? And thus began, this is the SNARK, the first artificial neuron. It took about six vacuum tubes to build it. Now, Minsky is interesting in this case because he looked at it and said, hey, because I can't implement XOR logic, then obviously one-level neural networks are a dead end. In his book, Perceptrons, along with his co-author, pretty much killed the neural approach for some time. But then there were discoveries of some interesting algorithms, backpropagation in particular, and limited Boltzmann machines, the latter coming from Hinton. And this was where we saw the renaissance in AI. These were happening in the 70s, 80s or thereabouts, the algorithms. And it wasn't until we had this perfect storm of lots of data, lots of computational power coming from GPUs, we could start doing some things. And some of those things, mostly in the area of neural language processing, led us to architectures such as BIRT, which was the dominant architecture for the longest time in just natural language understanding. Quite cool stuff. Now today we see the dominant architecture in that space known as foundational models. This is what GPT-3 is all about. This is what China has built. It's literally a multi-billion parameter model. This is what we see coming out of Google of late as well too. And this is what they've been doing for their translation systems, where the Google Translate sort of works behind this. So what you're beginning to notice here is that there are pieces of AI, but there's still a lot of other stuff that hangs around it. Now, the good folks at DeepMind had a little bit different approach. We saw this with their AlphaGo, and then they had a game-based version of it, and then an AlphaFold came of it later, which we see now, which was a marvelous thing. It's incredible architecture. There are indeed some very clever ways they prune the search space. They have basically trained some AIs to, quote, understand the physics of down at the subatomic level. But by the way, it's a pipeline architecture. So the way it works is they throw up some candidate protein folds. They test it in certain ways, and we're talking millions of them potentially. They test them, they throw some away, they refine them again. An awful lot like the Watson architecture, which was statistical. This one is neural under its basis. This, of course, has led us to a number of hardware things as well. And we see the TPU coming out of Google, and also NVIDIA, which is just crushing it on the edge. I have beside me a cloud running with four Jetson Nanos, and I've got more computational power that existed in the world back in the 80s, just sitting right here for $1,000. It's pretty amazing. But here's what's striking, that the AI community is beginning to discover the lessons of symbolic software engineering. They have begun to discover patterns of neural networks. And in fact, this is the most dominant architectural pattern, the transformer. This is really cool, and I urge you to go look at some YouTubes about it. Got some hairy mathematics associated with it, but it's the essence behind pretty much all the contemporary AI structures you see today. It deals with the problem of attention, that if I'm looking at a time series of things like a sequence of words coming in or a sequence of images, then I don't just look at one of them at a time, but I look at many of them simultaneously. So there's some interesting opportunities for concurrency, and it offered a tremendous increase in the way we deal with our systems. There's another interesting thing that we've discovered. Andreff, who is the head of AI for Tesla, observes, working with neural networks is a lot like looking with symbolic systems. You're just doing it, you're maintaining a code base. That code base is just alive like other code. And in fact, it is just as iterative and incremental as before. The difference being now that you've got not just continuous deployment, continuous integration, continuous architecture, you've got continuous learning. And so you use the similar structures as you would use today, you're just bringing in a different skill set along the way. So contemporary AI is about this. It's mostly pattern matching of signals on the edge, inductive reasoning, and these foundational models. But where we're not yet mature is in the area of using AI for decision making and abductive reason. Abductive reasoning is model building, which says I look at the world and I'm making theories about it and I build upon those theories. And part of that's related to causal reasoning, which are some of the ideas around, you'll see in the Book of Why by Judea Pearl. Marvelous stuff. So there's work to be done there. Most of the action is in the first part of this. There's some interesting research happening in the second part. So here's where they come together. Remember that symbolic methods of models of computation and AI ones are Turing equivalent. So that means I, as an architect, now have a choice. And oftentimes what I'm seeing in systems like this, it's not so much architecting the AI, but the problem is architecting the system that has an AI component. And most of those components end up being on the edge, or they are attached to a pipeline. So this is the common architecture I've seen where many of these pieces come together. Most AIs these days are some form of ANN or a CNN, or as I mentioned, transformer architectures. We seem to have some reasonable stability there, and that's probably going to last for a while. Most of the changes I see happening in the research side are mostly incremental, but those patterns are going to stick for us. So that means as an architect, wow, my palette's now bigger. I've got things that have very different kinds of latency, scalability, explainability, and risk profiles than I did before. So that's the presenting problem. It's less the engineering of AI and more so the engineering of systems with AI components. So I mentioned earlier that symbolic systems have grown largely because of real use. Neural models of computing have advanced due to this perfect storm. We have lots of data, we have some great theory, we have GPU computational resources, but it's largely driven by research challenges. Yes, Tesla is kind of an exception, but if you look at where most of the advances are, they're being fueled by those kinds of things. Not saying that's bad, but it's just different. And now there's a different model of computation, quantum. Hang on to your seat belts, put your seat trays in the upright position. It's going to get rocky here because this is pretty wild. As Feynman said, if you understand quantum mechanics, you're probably wrong. Indeed, it starts with Feynman. Feynman back in the 40s and 50s, a tremendous physicist, theoretical physicist, posited that it was possible to do computation at the quantum level. He observed that if we posit the notion of a qubit, which is not like our normal bits, but it's a unit of information that may be in an indeterminate state, I can act upon it. I basically, place it within some Hamiltonians. And I don't look at it until I'm ready for it to solve it, because once I look at it, then the quantum wave is collapsed, and that gives me the solution to it. So all of a sudden, you now see there's some really funky stuff happening at the bottom. It's not quite like Boole, where we can understand this stuff with truth tables. There's some really weird things happening at the bottom. David Deutsch came along in the 70s, I think it was, and he observed, building upon Feynman's ideas, that it was possible with qubits to actually build quantum gates. So we're now dealing with XOR, OR, and kinds of things, rediscovering that it was possible to do the same kinds of universal computing that we could do in symbolic systems and neural systems, we could now do in quantum systems. That's pretty cool. So as you remember that diagram I gave you earlier about vision to implementation, the world of quantum is still largely in the realm of physics to algorithms. So one of the first algorithms built in this space is Shor's algorithm. And this is why quantum stuff is so cool. It represents an algorithm that can do factorization. Why is that important? Well, factorization is essential to every kind of cryptology. And I'm not talking cryptocurrency, I mean the real cryptology. As I start encrypting things and decrypting things, we build them based upon the ability or the recognition that they are mathematically difficult to solve. Quantum computers changes this table stakes, and it says, oh, there are different ways to do this in much faster ways than we could do in our symbolic systems. And indeed, Shor's algorithm is what's key to that. So this is the realm in which quantum systems play. You may remember back from your classes in complexity, we've got NP problems, NP complete problems, NP hard problems, P problems that can be solved in polynomial time. Problem, of course, things like encryption. When I'm dealing with 256 or 512-bit hash, yes, I need more seconds than exist in the life of the universe with contemporary machines. But there is this thing called a BQP, a bounded quantum polynomial algorithm, which operates roughly within this space, which we theoretically understand and to a reasonable degree have proven that quantum computers can do really complex P problems in some amazing time. That's why quantum computing becomes interesting. And now, as I mentioned, it's still largely a problem of physics that we see systems like this. Now, you may say, what's all this funky wiring here? Well, there's a reason. You've got to keep quantum computers very, very cold. You may remember from your physics also that the average temperature of the cosmos is about 3 degrees Kelvin. Now, you may say, why is it so hot? Well, of course, that's very cold. And the answer is that's the remnants of the heat from the Big Bang. That's what's left over from billions of years ago. But there is sufficient energy in even 3 degrees above Kelvin to destroy a quantum wavefront. So when you're dealing with a quantum computer, a qubit, you have to actually cool it to around 0.3 3 degrees Kelvin. And anything above that, then it tends to be very, very noisy. Noise is the key problem that we're dealing with here in these kinds of systems. Let me give you an example. I hope this is new to some of you. This is an example of Shor's algorithm. This is what it looks like if I'm doing the factorization of a number. And these are the kind of diagrams you would see if you're programming a quantum computer. But obviously, you're not going to program it exactly like this. This is the language you'll use. This is Qiskit, a language which has been developed at IBM, and it's Python-like, and this is basically how you would program a quantum computer. Now, that's the Shor algorithm right there. An important observation. Calling it quantum computing is a bad idea. Jay, who is a fellow who leads our quantum work at IBM, observes that's a bad name because there's no computing taking place. It's more quantum processing taking place. So it's better to think of quantum computers more as coprocessors like we had back in the 70s or 80s or so that do certain kinds of calculations very fast for us, and we have to wrap that in some other package. And as you see here, you basically do this offline. You ship this calculation over to your quantum computer. You don't look at it for a while, and then poof, you get it. In fact, this is where a lot of the research is taking place right now, and most of it has to deal with error tolerance. You have to build systems of a certain size that you can have a reasonable level of confidence that the calculations you're doing are relatively error-free. So that's where a lot of the calculations are taking place. By the way, it's important also to look on the left-hand side. You're aware of the software stack you use within cloud systems. This is the software stack you'll see within quantum systems. That we're dealing mostly with algorithms these days. There are a few that we know solidly and we've simulated them quite well, and we're now trying to bring those to reality to our systems. In fact, you will soon see this notion of quantum computing as a service. IBM, Amazon, Azure are all trying to do it, putting it on their various clouds. So it becomes another tool in my quiver, if you will, in my toolbox as an architect. So quantum computing has advanced largely owing to theoretical possibilities and the limitations of von Neumann architectures. This is what's moved us along the way. So now we can bring this all together. What does software architecture look like for us in a post-AI and a post-quantum world? Well, it's my observation, having been working in all three of these, which is a wonderful privilege to be able to do. Symbolic computing is going to be augmented, but not really replaced by the neural and quantum models. The fundamentals are still going to remain. All the things we've talked about here in terms of abstractions and coupling and cohesion, they don't go away. The fundamentals are indeed fundamental. There's a lot of work to be done in the representation of these mixed model systems. I don't quite know how to present to somebody other than on a whiteboard. What does a quantum processor look like coupled together with a transformer architecture together with a large database? Work to be done, but we're building such systems, and it's hard. There's work to be done in orchestrating the life cycles of these as well too. Although what we see happening in the neural world gives us positive indications that what we've learned in the symbolic world will still apply. And there's much to be done in the world of tooling for all of these as well too. The world for web-centric systems of scale, there's lots of tooling. We're a long way to go in these other domains. So I'll begin to wrap it up here. Alan Newell, you heard me mention him earlier, back in the symbolic days, said this: computer technology offers the possibility of incorporating intelligent behavior in all the nooks and crannies of our world. With it, we can build an enchanted land. We as architects are in a very privileged place because we help build that enchanted world. So in that sense, we are in a place of abundant computational resources. Nothing's forgotten. We're connected in pervasive, unexpected ways beyond our choice. It's reasonable to stop and think, what kind of world do we want to create? This is an amazing landscape, an amazing palette with which we can paint. And as architects, hey, this is a lot of fun. There you go. So I think we may have, here's how to reach me. So feel free to do so. Every time I gain a Twitter follower, an angel gets its wings. So I'll bring it back to you all.
Oh, okay. Okay. Grady, that was an awesome presentation. I have I guess, a question for you going forward. Sure. I can imagine that, in these architectures, you're going to have emergent properties that we don't deal with today. You talked about things like sentience and things like that. Do you see that you're going to need to modify something like your 4+1 architecture model to deal with that and, represent some of those properties? Or is that going to be enough going forward since we're just bringing things together?
Funny you should mention that. The short answer is, thus far, the 4+1 model view and about 10% of the UML has been sufficient to do what I want to do. So I alluded to this project earlier, and this is why you see all the robots around me. This is a pepper. I've got a now sitting here beside me. I've got some wheeled robots and the like. We were doing some work for the Johnson Space Center and literally on the mission to Mars effort, in which I developed a neural symbolic architecture that brings together the ideas of Minsky's society of mind, together with Rodney Brooks's concepts of subsumption architectures, and then basically transformer agents behind them. And the UML and the 4+1 model view was sufficient to do what we were going to do. So I was surprised and delighted.
I have another question. This is sort of personal. When I did my master's thesis, I was looking at planning. And that becomes an exponentially, multi-goal planning becomes exponentially hard at some point. Mm-hmm. And it took hours. Do you see that we may be able to have algorithms in the quantum neural world that change the game? Like you were talking about MP complete problems, and it looked like there was a class that you could solve in polynomial time using these algorithms.
Yes. So yes, I believe that is the case. And this is why I say the future is so bright. There are so many amazing things we have yet to be able to do with software. So yes, I think we'll get there someday. Not tomorrow. Not like what Kurzweil would say. It's going to be in 20 so and so. I think. Don't get me started. But yeah, not anytime soon.
Final question, Grady. As a next step, I sort of had gone through these AI winter periods you talked about, and here we are today. And if you were to say, okay, this is an area to look at, this is what you need to learn to come up to sport, where would you direct people to go?
Great question. We weren't certain as a community if we were going to hit an AI winter again. I think we've reached an AI plateau in a sense that we find folks we're seeing incremental changes to a lot of the stuff with deep learning. That's cool. But even Hinton has recognized that there are limitations to it. Gary Marcus and I are constantly beating up on the open AI guys on Twitter about how the system doesn't yet understand. So we know there are limits. But even so, we know that with the kinds of deep learning systems that exist, you can do some incredible things. And that's different than what we saw in the previous generations, that there is real business value in some of the things going on here. So that's the good news, which is why I'm not seeing a winter. Therefore, back to your question, what would I study? There are so many great books, so many great YouTube videos. Go dig into the transformer architecture. Start there. Find some videos about that. And first time you watch one of those, you're going to say, my God, there's so much I don't understand. But that will lead you to maybe dive into the next pieces. Well, and on the quantum side, Qiskit has publicly available a simulator. So go sign up for it.
Who's that, Grady?
Qiskit, Kiskit.
Okay.
It's a simulation system that IBM has.
I have a ton of questions, but we're out of time. I really appreciate this.
Sure.
This is awesome. Thank you so much, Grady. This has been, for me, this is an awesome presentation. Thanks so much.
Thank you. Since I'm in Maui, I'll have to say aloha. Bye now.
Aloha. Excellent. Thanks.